Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today we're thinking about the area of a circle. And recently we went around our yard looking for objects that were circular, and we've used cylinders because their bases are circles, or spheres, like this basketball. For today's activity, you're going to want to look for something cylindric, or maybe a cone, something that has a base of a circle, versus a sphere. The cross-section of a sphere is a circle. Any cross-section of a sphere makes a circle or a point at the very end. But you're not going to want to use this for today's lesson because unless you want to cut something, but I'm not going to cut my basketball in half. So if you have an orange, maybe that'll work, but you definitely need something that creates this flat, two-dimensional base of a circle. And unless you have a sphere that you can cut, like we cut the orange, you could cut the orange and trace the cross-section you get, or just find a sphere and trace that. Sorry, not a sphere, a cylinder and trace that, because you can lay that flat on a piece of paper. And that's what I did.
Before we begin the activity, it's important that we take some time to clarify terms and concepts that will be referred to during the activity. First, circumference is the word we learned last week. It's the distance of the collection of points that form the circle. So if you were to take a circle and unhook it and straighten it out, what is the distance of that line that wraps around the circle? That's the circumference. We saw that last week. It's a one-dimensional measure of length. This week we're talking about the area of the circle. So the area of the circle is the number of square units needed to completely tile the interior of a circle with no gaps and no overflow. More generally, the area of a two-dimensional shape is the number of square units needed to completely tile the interior of a shape with no gaps and no overflow. You can see here the hexagon. I'm counting the number of squares that tile the hexagon, but I'm not necessarily using the graph paper because it doesn't always line up the way I want it to. And so we saw before with the area of all these circles that the smallest circle on the inside has a 2x3 rectangle in the middle, so that tells us it's a little more than 6 square units. And then we have 7, 8, 9, 10. I would say it's about 11 square units, that center area of the circle. But when we come over here, my square unit changes. It looks like these gray squares are about 9 of the squares from the paper grid. But you can decide whatever size square you want to use to tile a surface to call it square units. And then if you want to be more specific about how big that unit is, you can, but a square unit can be a square of any size. And here it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'd say about 13 square units. Would you agree? Notice that when we call the area of a shape, we say the unit of measure is square units because we're tiling a surface. We're finding the area of something, how big the surface is, versus circumference, which is the distance of a straight line. The units of length, one-dimensionality, like circumference, are just called units. There's no squared, okay, it's just a single dimension unit. So the diameter of the circle is the distance across a circle from one point on the circle through to the center to another point on the circle. So we're starting on one edge of the circle through the center point. The center point's important, all the way to the other edge of the circle. And we are using diameter as a way to calculate circumference because the diameter wraps around the outside of the circle a little more than 3 times. And that little more than 3 times value is called pi. And we'll see pi again this week in determining area. Remember that pi is the irrational number formed by dividing a circle's circumference by its diameter. It's approximated with a rational number value of 3.14 or 22/7. This image shows the distance of pi wrapping around the circle about little more than 3 times, 3.14 times. This week, we really need to understand radius a little bit more because radius is half the diameter, and radius has a very special relationship to the area of a circle, much like the diameter had a relationship to the circumference of a circle. The radius of a circle is the distance from the center to any point on the circle. This is half the distance of the diameter. Now we can start to think about pi as the irrational number formed by dividing a circle's area by a square with side length equal to the radius. So that's a heavy definition. Basically, look at this image and you'll see that there are 4 squares that are required to enclose the circle inside of it. So we use 4 squares. Those squares have side length of the radius. So the radius is the side length of each of those squares, the radius of the greatest circle in these concentric circles. And you can see that it's less than 4. How much less than 4? Well, I'm going to guess that it's 0.86 less than 4, because 4 minus 0.86 is pi, 3.14, or our approximation of pi. Pi is a ratio, but we use values to add pi or multiply by pi in certain formulas related to geometric objects, including circles. So here you can kind of visually see that a square formed with a side length equal to the radius of a circle will tile the surface of the circle pi times. And you see that it's about 86% left over on the outside of the circles because you don't need all 4 squares. You need less than 4 squares, and actually 3.14 squares. Okay, continuing on. Thank you for joining us. I want to speak quickly about dimensions. So the reason I talk about dimensions is because we use all of these ways of describing the world around us in the four different dimensions that we have here on Earth. So 0 dimensions is a point or a location, and it's important for circles because that center point helps us determine where to measure the radius from and the diameter from. The circle is formed by points that are equally distant to that center point. So that point, that 0-dimensional component of a circle, is very important. 1 dimensions, a line, a distance, and we see that the circumference of a circle is that 1-dimensional measurement of distance for a circle. It's the length of all those points forming that shape, that perfectly round shape that we know as a circle. 2-dimensionally, what we measure a circle 2-dimensionally with is square units. And you see here that this perfect 4x4 square fits into this circle in the top left image. And so it's going to be more than 16 square units here. How much more? Why don't you decide? I would probably say 24 square units. Now, volume, if you look down at this image of Saturn, it lets us know how many cubic units fill a 3-dimensional space. So if you have a sphere, how many little tiny cubes or big cubes would fill this region, and that would be the volume. Now, we also can get 2-dimensional interpretations of 3D objects with cross-sections, and you saw that in our last video with the orange slice, but I want to encourage you to think about cross-sections of cylinders, cross-sections of cones, and cross-sections of spheres in order to complete the activity this week. So here's a cone. It has a circle base and it forms a point at its apex. This is a cone. So what cross sections of the cone would form a circle? Here's our cylinder, two circle bases, and a rectangle connecting them for the height, and then a sphere. So these are all 3-dimensional solids that have circular cross sections, and you could use any of those for your activity this week.
Area is the number of square units that tile a surface. So that's, again, why we're not using a sphere, because this is a curved surface and we can't use squares to tile it, because you'll see that the squares kind of get warped, and it's kind of cool using a silicone mat to see that like a square is not going to lay flat on a sphere. We need to think about two-dimensional circles. Two-dimensional circles, even in real life, this you might think is two-dimensional. It's flat, right? But it's not two-dimensional. Everything in our world has 3 dimensions. So circles are like this kind of theoretical idea, because we can't actually have 2 dimensions. Even if you have a piece of paper, okay, that's not two-dimensional. It's very close, but there's still thickness to it. An area measures 2 dimensions. The cool thing about silicone squares and Post-it notes is that we can trace them. So when you trace something on paper, it kind of creates that theoretical two-dimensionality. The ink doesn't really have thickness, right? So we can use the ink to represent what a two-dimensional square or circle would be. So looking at this Pyrex container, you might agree with me that the lid is about 1 silicone square. It's less than a silicone square, obviously, because we have these pieces, these corners hanging off the edge. But if you lay the Pyrex on the silicone square, you can kind of see that the circle fits exactly inside the silicone square. And that's pretty ironic. These are just objects I have in my house. So I encourage you to find some circular cylinders or circular objects in your house or backyard and some squares. The 2 squares I chose were a silicone mat used like a trivet and Post-it notes. So my silicone square, I luckily have graph paper at home, so you don't need to do this extra part, but if you have graph paper, you can do it. And I counted that my silicone square is 900 squares, and this graph paper is 1/4 inch by 1/4 inch. Or if you looked at 4 squares, that's 1 square inch. Or 1 inch squared. So why do we care? Well, we can measure in 1 inch squared or 1/4 inches, or we can measure in silicone mats, or we can measure in Post-it notes. So what you're going to do at home is find something circular and find something square and try to estimate the area. So you can start big. This is about 1 silicone square as area. Or we can look at Post-it notes. So if we have Post-it notes, how many Post-it notes would tile the Pyrex?
Here I line up the 2 corners of the first Post-it note with points on the circle and then tile the rest of the Post-it notes from there. I have to rip up a Post-it note, and I end up using about 4 Post-it notes to tile the circle.
I think that's good enough. So I would say that with the wind blowing, this is about 3/4 of the 5th Post-it note that I'm using to tile the Pyrex lid. So I'm going to say that the Pyrex lid is 1 silicone square, or it's 4 3/4 of a Post-it note. Now, which one's more accurate? I think that the Post-it note approximation is more accurate because there's not anything hanging over, theoretically, and what I'm probably a little bit under here in this estimation because there's a lot of red showing, versus my square, which takes over it's extra. There's more area in the square than there is in the silicone mat, where I think 4 3/4 of a Post-it note is a little short of the actual area. So then what I did is I took the Pyrex and I traced it onto my graph paper, and I also measured the silicone mat and the Post-it note using the graph paper. So one Post-it note is 144 squares. That's 1 square on this graph paper is 1/4 inch by 1/4 inch. So that means that 4 by 4 of these grids makes 1 square inch. So I'm not worried about the square inches so much. I'm more curious about which one of these is more accurate. Is it the silicone square or is it the Post-it note? And you'll see that a Post-it note is 144 squares on the graph, and the silicone square is 900 squares on the graph. Okay, to estimate the number of squares on the graph that fill the Pyrex lid, I used a series of rectangles. So I looked inside the circle and I colored in the rectangles that I could form without any of the corner squares being chopped off. So these are full rectangles that can fill the inside, and I recognized that it was symmetric. So if it was symmetric, I only had to count half of them and then I could double it. Once I figured about that half of the circle was filled with 328 squares, I went around the edge, the white remaining parts, and counted approximately which pieces would fit together to make about one square. And I got about 11 on each of the 4 sections, if we kind of broke this into fourths. So 11 times 4 is 44. 328 times 2 is 656. The sum of those two is about 700 squares. So I estimate that this is filled with about 700 squares. Which one is more accurate? Well, you'll see that 900 squares is 200 away from 700. So that's a 29% error. And this little post-it note, 4 3/4 of those, well, 4 of those is 576 squares, and then 3/4 of 144, 3/4 of 144, or 75% of 144 is 108. So this approximation of 4 3/4 post-it notes comes out to 684 little squares. 684 is only 16 little squares away from the approximation I used by coloring in the circle. So that is only a percent error of 2. So that's pretty cool. What you could do if you have the tools, you could measure your actual circular object and calculate the area of the circle using an equation. So I hope you notice here that using squares is not really an efficient way to calculate the area of something because it's not very precise. So luckily in mathematics we can create expressions and equations to help us generalize patterns and calculate more precisely what measurements are. And that formula is the area of a circle is the ratio pi, which is circumference over diameter, times the radius squared, which means multiply the radius by itself, so radius times radius. Okay, so we can use the approximation of 3.14 for pi, and we need to measure the radius of the Pyrex lid. So again, I love the Pyrex because it has this little center mark. I know exactly where the center is. And then I'm going to use inches to measure from the center to a point on the circle. You know what, I'm going to just go ahead and write on here for you all, like I did in the circumference video. So that is our radius, and it looks like it is 3 inches, and that's a half, or 8/16, 7, or 8, 9, 10, 11/16. So it's 3 inches and 11/16. So our formula is that the area equals pi times r squared. So that's going to be approximately equal to 3.14 times the radius, which is 3 11/16 inches squared. Since this is a decimal, I know another approximation for pi is 22/7. So I'm going to use that instead of the decimal because I'm dealing with fractions here in inches and feet. So 22/7 times, now I'm going to convert 3 11/16 into an improper fraction. So 16 times 3 18, carry the 1, 48. So that's 48 plus 11 is 59 sixteenths times 59 sixteenths, because we have to do it twice from the squared. 3 and 11 sixteenths times itself. Okay? So now we need to see if there's anything we can cancel out. So I know that 22 and 16 are both multiples of 2, so I get 11 over 8. And 59, I don't know anything too friendly with that. So if I'm going to do 59 times 11 times 59, okay, I'm just going to round these. I'm going to go, instead of 11, I'm going to go 10 times 60 times 60 over 7 times 8 times 16. Okay, so then I get 3 zeros. These are definitely approximate. Okay, 3 zeros. And then 1 times 6 is 12. So I get 12,000 divided by 7 times 8 is 64 minus 8, which is 56, times 16. 56 times 16 . 896 is about 900. The zeros will cancel, and I have 120 divided by 9. Goes in once, subtract the 9, I have 30 left over. It goes in 3 times is 27. I have 3 left over and 1/3. So the area is approximately equal to 13 1/3 square inches, because we multiplied inches times inches, which gives us inches squared. Okay, so what is that in little squares? Well, 1 square inch is 16 little squares. So I can figure out how many little squares the area of the Pyrex bowl is by multiplying 13 1/3 by 16. So 13 times 16, carry the 1, 7, placeholder 0, 3, 1, 8, 208. And then 1/3 of 16 is 16 divided by 3, which is 16/3. And 3 goes into 16 5 times with 1/3 left over. So it's 2, and we add these two together, so we get 213 1/3 little squares. Does that make sense? Is that 700? No, that is not 700. So where did we go wrong? So let's see what we get when we calculate with a calculator. Maybe we can find the mistake. So we have that the radius, maybe we measured the radius wrong. So I'm going to just say 3 3/4 instead. So we're going to go with 3.75 inches times 3.75 inches times pi 3.14 is about 44 square inches. So we definitely went wrong in our calculation somewhere. We'll see if we can find out where. And then if I multiply that by the 44 square inches by the 16 little squares that are inside, I get 706. So my estimate using the rectangles that fill the inside of the circle is super, super close. Okay, the actual area of the circle is 706.5 little squares, or 44.1 inches squared. but in each inch there are 16 little squares, and so that's 706.5 little squares, and I counted 700. So if the actual is 706.5, I can find my percent error by dividing 6.5, the difference between the two measurements, by the actual. So 700 was my estimate. The absolute value of the difference between the estimate and the absolute value of the estimate and the actual areas of the Pyrex lid is 6.5, and then I'm going to divide that by the actual area. So I'm going to divide that by 706.5. It's going to be a really small number. It's a 6 divided by 700. It's going to be a teeny tiny percent. So 6.5 divided by 706.5 is 0.009. So what is that as a percent? Well, to get this decimal to be a percent, I move the decimal place twice to the right, or I think about the hundredths place, and so I get 0.9%. So this is less than 1%. So I had less than 1% error using my rectangle strategy in estimating the area of a circle. I hope you enjoyed this quick tutorial about what area is and why we need a formula like pi r squared to help us calculate it for circles, because circles and squares don't have the same characteristics. Circles are round and squares are rigid and have right angles. So it makes sense that it's not very natural to fill a circle with squares. So we use this formula, area equals pi times r, or area equals pi times radius, or area equals pi r squared. And we use this formula to help us determine the area, the surface, the size of the surface of a circle. Around your house, find a circle, find little squares. You can use any type of square. See how many squares fill that circle, and see how close you can get to the actual. Grab a calculator. See if you can measure. Grab a measuring tool. I know a lot of phones have apps that can help you measure, and see how accurate you can get your estimation using square objects and using the formula. Thanks for tuning in to Muddy Math. I hope this was helpful. Visit my YouTube channel, Muddy Math, for more tutorials. Were you able to find my mistake in my calculations using fractions? I was curious, and I went back and I found it. I said that 10 times 60 times 60 was 12,000. Is 10 times 60 times 60, is that equal to 12,000? Well, what's 6 times 6? 6 plus 6 is 12. What's 6 times 6? 36. So I really needed 3,600 here. I'm sorry, 36,000. So my answer is 3 times smaller than it has to be. So my answer here should have been times 3, which will turn out to be 40, which is what we were looking for. Because then 40 times 16 is much closer to 700 than 13 1/3 times 16. So if I did 40 times 16, I get 4 times 4 is 400, and then 6 times 4 is 6, 12, 18, 24. It's 240, so then I would have gotten 640 little squares from my estimate, which is less accurate than the 706.5, but it's still way, way, way closer than 213 1/3. Okay. I hope you enjoyed the little blooper. I hope you enjoyed finding my mistake. Mistakes are beautiful. It's how you learn. Find the struggle. Push through it. You got it. Signing off.